Hi, I'd like to read you Chapter 7 of the book Stuff, subtitled The Fortunes, Foibles, and Fiascos of Those Who Sought to Understand Matter. Chapter 7 is titled John Dalton, or Revenge of the Atomists. The 1700s were about shot, and people still didn't know what stuff really was. All the pieces of the puzzle were on the table waiting for someone to put them together. There was only one way to put them together that made sense, and John Dalton saw it. For a famous science guy, Dalton had fairly unpromising beginnings. He was born in 1766 to a poor family in the small town of Eaglesfield, England. It wasn't much of a town then, and it still isn't. Here is a picture of downtown Eaglesfield, England, John Dalton's hometown. Someone had put up this sign on the house where he was born. Not much has happened there since. John Dalton's father had a hard time supporting his family with his earnings as a weaver. Have you ever heard of a rich weaver? To help out with the family finances, John went to work at the tender age of 12 as a teacher. When he was 15, he joined his older brother, Jonathan, to teach at a Quaker school. They taught there because the Daltons were Quakers, a Christian sect that many people in England found annoying at the time. They were called Quakers because they sometimes quaked during their church services. They were also called dissenters because they broke the rule that everyone had to belong to the Church of England. They called themselves the Society of Friends, or simply Friends. Being a dissenter meant that many colleges wouldn't accept John as a student. This limit on his educational opportunities may have changed the course of his career, but it didn't seem to limit his ability to dig deep into the true nature of stuff. The names of these products suggest that Quakers discovered oatmeal and motor oil, or maybe not. Dalton earned most of his money teaching, lecturing, and writing. In his spare time, he made major contributions to several fields of science, including chemistry, physics, and meteorology. In 1801, he discovered the law that is stated, in a mixture of gases, the total pressure is equal to the sum of the pressure of the gases that make it up. The law was such a hit they named it Dalton's Law. He also was the first to study color blindness and published an article on the subject when he was 28. His interest in the topic was due to the fact that both he and his brother were colorblind. The upside of his condition was that he didn't mind that Quakers frowned on colorful clothing. John Dalton's biggest achievement, however, was his atomic theory. Around 1800, these things were known and generally accepted regarding the nature of matter. Matter is never gained or lost in chemical processes, the law of conservation of matter. Elements are materials that cannot be further simplified. Elements combine to form other pure materials called compounds. Compounds are made up of the same ratios of elements by mass, the law of definite proportions. As we saw in the previous chapter, Antoine Lavoisier was largely responsible for laws for 1 and 2. Laws 1 and 2. Law 3 was discovered by the French chemist Joseph Proust. There are many examples of this law. For example, the ratio of the mass of hydrogen to the mass of oxygen in water is always 1 to 8. To these, Dalton added the law of multiple proportions. If two elements form more than one compound between them, then the ratios of the masses of the second element which combine with the fixed mass of the first element will be ratios of small whole numbers. Confusing, right? It's much easier to understand from an example. Carbon and oxygen form two compounds, carbon monoxide and carbon dioxide. Now it is time to talk about chemical formulas, even though we're getting a little ahead of Dalton. Carbon monoxide has the formula CO. Carbon dioxide has the formula CO2. C and O are chemical symbols for elements, carbon and oxygen. The little 2 dangly called a subscript means that there are 2 oxygen atoms bounded to each carbon atom. If there is no subscript, it means 1 atom. So CO2 has twice as many oxygen atoms bonded to each carbon as does CO. For example, 7 grams of carbon has 3 grams of carbon and 4 grams of oxygen. 11 grams of carbon dioxide has 3 grams of carbon and 8 grams of oxygen. The ratio of the masses of oxygen in the 2 compounds is 8 to 4, or simply 2 to 1. Dalton thought about these 4 rules of matter and came to the conclusion that matter had to be made of atoms. This was a brilliant bit of logic that is not easy to explain. And maybe this will help. Think about a bicycle as a compound made of 1 frame, call it F, and 2 wheels, call them W's. The formula would be FW sub 2. If you start taking identical bicycles apart, you find that the ratio of the mass of the wheels to the frame is always the same, the law of definite proportions. If you take a wheel apart, it is no longer a wheel. If you take a frame apart, it is no longer a frame. Elements cannot be further simplified. After the piles of wheels and frames are put back together, you will have the original group of bicycles with no parts left over. The law of conservation of mass. Throw in unicycles and tricycles, and you have the law of multiple proportions. Think how much harder these logical steps would be if bicycles were invisible. That was the kind of problem Dalton solved. It's as if he figured out that bicycles always have 1 frame and 2 wheels, even though he had never seen one. Dalton summed up his atomic theory in 5 simple sentences. 1. Elements are made of very small particles called atoms. 2. All atoms of an element are the same, and different elements have different atoms. 3. Atoms can't be broken up into simpler bits. 4. Atoms of different elements combine in simple ratios to form compounds. 5. In chemical reactions, atoms are rearranged. After more than 2 centuries, these statements are all still accepted as true. Well, sort of. They are all true for ordinary chemistry, but numbers 2 and 3 aren't always true when you consider nuclear reactions. But give John a break. Many perfectly good theories only explain nature within certain boundaries. When you try to apply a theory to a bigger picture, you often need a broader model. You think his theory was simple. Take a look at his atomic model. You can't get much simpler than that. This might have to do with his being a Quaker. Quakers like to keep everything simple. Simple clothes, simple food, simple lifestyle. It's a joy to be simple is one of their favorite songs. John Dalton also thought science should be simple. It may have been because he was a Quaker, but maybe not. Many scientists believe that when trying to solve a scientific problem, try the simplest answer first. If you think about it, you will see that many of the important laws of science are quite simple and can be expressed as uncomplicated equations. For example, F equals ma, E equals mc squared, etc. Here's a picture of Dalton's atomic model. It's about as simple as you can get. Unfortunately, John carried his love of simplicity too far. He thought that atoms of different elements combined one to one. He knew that water was a combination of hydrogen and oxygen, so he said the formula should be HO. Now we know that it is H2O. Based on how he thought elements combined, he came up with a list of relative masses of the atoms of elements. He decided to give hydrogen a weight of 1, then used combining ratios to get the weights of the atoms of other elements. He got them all wrong. One thing that threw him off was that he didn't know that many gases are present as two atom molecules. The formulas of hydrogen and oxygen aren't H and O, they are H2 and O2. We're not going to list his atomic weights because you might remember them, and this could lead to poor grades on tests. Here is a picture of John Dalton wishing life were simpler. Some other scientists of the time didn't trust Dalton's conclusions because they said he had a sloppy lab technique. They may have thought that this because they thought John was too poor to buy good equipment. This may be true, but when other scientists repeated his experiments with their fancy schmancy equipment, they got the same results. The feeling was mutual. John didn't trust the results of other scientists either. He always repeated other people's experiments before he used their results as part of his studies. He didn't like some of the new theories either. He often refused to accept new ideas when everyone else thought they sounded okay. He didn't even like the new way of writing chemical formulas with the symbols and the subscripts. Instead of writing carbon dioxide as CO sub 2 like everyone else, he stuck with his old system and wrote white dot, black dot, white dot. But we should excuse him for being stubborn and give him a big hand for the good job he did on his atomic theory. After 2,000 years of confusion, he nailed that theory down and changed the understanding of matter forever. It seems odd today that atoms weren't accepted as real things overnight. It actually took a little over 100 years for all respected scientists to get on board. The doubters seem to be struggling with the same philosophical misgivings that bothered Plato and Aristotle way back when. They didn't like the idea that everything that happened was the result of little invisible balls bouncing around. In 1895, Wilhelm Ostwald said that the atomic theory wasn't even a useful hypothesis and that it was simply a mistake. Ostwald was no hack. In 1909, he was given the Nobel Prize in Chemistry. In 1910, Alexander Smith, a chemistry professor at the University of Chicago, said that the atomic theory was handy as a way of symbolizing chemical reactions, but it didn't prove that atoms really exist. Sometimes you really have to rub people's nose in a new idea before they accept it. 100 years of nose rubbing does seem like a lot, though. And that's the end of chapter 7. If you'll scroll down, you'll see a link to a place where you can buy the book and read reviews of the book and so forth. The next chapter I read will be chapter 8, Kinetic Molecular Theory, or the Polish Science Oscars. And if you look down towards the bottom of the screen, you should be able to find a subscribe button that will let you subscribe to the videos in this series. Thank you and goodbye.